Welcome back. In the previous lecture, we have been looking at ordinary differential equations and showing existence of solutions to first order system of ODE, and then we showed a similar thing for a 2-point boundary value problem for a second order ODE. In this lecture, we are going to look at the stability result of a 2-point boundary value problem that relies on the functional analysis results, which is the open mapping theorem. So we will prove that result and as a consequence derive the stability of the 2-point boundary value problem. Okay, so we'll start with the definition of an open map. So what is an open map? If you have two topological spaces with say different topologies, right? So X has a topology and Y has a topology different from X. Then we say a map T is open, which is from X to Y, is open if the image of every open subset of X is an open subset of Y, right? So if you take any open subset in X, then the image of that open subset under T is an open subset in Y. Okay, that is what is called an open map. So we'll first prove a lemma where we have a space, Banach space X, which is a complete norm space X, and Y is a norm space, right, which is not necessarily complete. So X is complete norm space, Y is norm space, and T is a bounded linear operator, right, which means so Bxy is the notation for bounded linear operator. You can also we also use Lxy, which is the set of all bounded linear operators, right? We have bounded linear operators from X to Y, which means it's a linear operator and it's also a continuous. So it's linear because X and Y are vector spaces. So it's a linear map and there is a topology in both X and Y, which is coming from the norm, right? From kind of both X as M. So X and Y both have some norm. So according to, so with respect to the norm, we have a topology. So corresponding to that, all those topology, this T is continuous. That's what we mean by continuous linear operator. So T is a continuous linear operator such that if you take, so here BRX0 denotes the ball of radius R centered at 0. This X basically denotes that this is a ball of radius R centered at 0 in X, right? So the superscript will denote in which space we are considering the ball. So BRX0 image of that, which is in Y now, closure of that contains the ball of radius S centered at 0 in Y. Okay, so whenever this happens, then actually T of BRX0 contains PS. So here we say if the closure contains this, then the set itself contains that. Okay, so to prove this, first we observe that it is enough to prove this result when for R and S equal to 1, that is for unit balls, right? Because you can do the dilation by the linearity, the dilation will work, right? So it's dilation invariant. So it's enough to prove this result. Whatever argument that we give for unit balls can be extended to balls of radius R and S. So you take a Y in the unit ball. So we take a Y. So we are taking S equal to 1. So we now take an element Y in B1 Y0. We need to show that that Y belongs to the image of this ball. Okay, that's what we will prove. So now you choose an epsilon such that now this Y is coming from the unit ball of Y. Y is coming from the unit ball of Y. So we choose an epsilon such that norm of y is less than 1 minus epsilon, right? So you choose an epsilon because norm y is less than 1, so you choose an epsilon such that norm of y is strictly less than 1 minus epsilon, and you define z to be 1 minus epsilon inverse of y, right? So you dilate that, right? Basically, now norm of z is also right. Norm of z is norm of 1 minus epsilon inverse of norm of y, which is less than 1, which is right. So now you define the set E, which is just T of b1 x0 intersection with b1 y0. So basically, this set that we have here, we need to show that this contains this. We look at this intersection of this set and this set. If this contains this, then the intersection will be this set itself, right? So that's what we need to prove. So let's take the set E, which is the intersection of the image of the unit ball of x and the unit ball of y, right? Now this set is non-empty because trivially 0 belongs to this set, right? Because 0 is here and image of 0 is also in this image set, so 0 is there. So this set is non-empty, is clear. Now E closure is B1 closure of 0, right? Why so? See, E is this, so the closure of E by this hypothesis that we have here, that TB closure contains this, so the closure of this contains this ball, which means that the closure of this is actually closure of this set, right? Because the intersection of this is precisely this BSY. So closure of that is closure of this. So E closure is the unit ball in Y closure, right? So that's what we have said here, which where we have used this fact, this assumption that we have had, right? So E closure is B1 Y closure using the hypothesis. Now you start arbitrary. You start with some point. So we are going to construct a sequence. So the first term in the sequence, let's call it Z0, is the origin. Okay. Now we are going to choose the next term in the sequence. So if Z0 is 0, now since whenever Z belongs to B1 0, this Z is what we have chosen here, right? This is the dilation by 1 minus epsilon of Y, right? This is in the unit ball by the way we have chosen here, right? Norm of Z is less than 1, right? So this is in the unit ball. So Z is in the unit ball, right? And E is dense in this ball because E closure is this unit ball. So E is dense in the unit ball. So if Z is in the unit ball, one can find a Z1 in E, which is a epsilon distance. This is by the density, and this epsilon is the one we have already chosen. Okay, this is by the density of E in the unit ball. So we started with Z0 0. Now we have chosen a Z1, which is epsilon distance from the Z that we started with. Okay. Okay. So now if you notice here, so this Z1 is in the epsilon ball centered at the Z, right? So by translation and dilation, you know that the Z, which is in the so the Z is in the epsilon ball centered uh, centered at Z1, right? Epsilon ball centered at Z1. So Z belongs to epsilon ball centered at origin translated by Z1, right? They are same, right? Whatever we have said here in this inequality is what we are saying here. So this inequality implies this condition that Z belongs to this. But this ball is just the dilation of the unit ball by epsilon, and E is dense in that, which means epsilon E is dense in this ball. So epsilon E plus Z1 is dense in this ball. So we have a Z. So the Z that we started with is now in this new ball, and in this ball epsilon E plus Z1 is dense, which means now for this Z, by this density I can choose a Z2. So now we are going to choose a Z2, in Y such that Z2 minus Z1, that is Z2 belongs to this set, which means Z2 minus Z1 belongs to epsilon E, right? Such that norm of Z2 minus Z is epsilon square. By the density, we can choose a Z0 such that this happens by the density of this epsilon E plus Z1 set. Okay. So proceeding in this way, at every instance, I can choose an element Zn such that Zn minus Zn minus 1, Zn minus Zn minus 1 belongs to epsilon n minus 1 E, and Zn minus Z is less than epsilon n, right? Because at every stage, you would have shown that Z is in this translated set, and epsilon n minus 1 E is dense in that set, whatever argument we gave here, right? So if we do this progressively, we have a sequence Zn in Y, right? Starting with Z0, 0, we have a sequence in the norm space Y. Now, by the definition of E, right? E was the intersection set, right? If you remember, E was the set intersection of this unit ball image and the unit ball in Y. So, by the definition of E, there is a sequence Xn such that Txn is 1 over epsilon n minus 1 Zn minus Zn minus 1. Okay. Here, from here we are saying, right? So we every time we have chosen things from E, right? Epsilon E. You see, Z is in this set, and we have chosen Zn minus Z in epsilon power n. So using this fact that this is dense in this, and by the definition of E, we actually have a sequence Xn in the unit ball such that T of Xn is this Zn minus Zn minus 1. Okay, because Zn minus Zn minus 1 belongs to epsilon n minus 1 E, right? Which means epsilon n minus 1 inverse of Zn minus 1 belongs to E, right? Now use the definition of E, which means there is an Xn such that this happens. So now you set your X to be this series epsilon n minus 1 Xn, and where this Xn is chosen, this one. So now let's look at what is this norm X, right? I mean, for this has to be well defined, this has to be convergent and so on. The series has to converge and so on, right? So what is norm X? So this norm X is less than or equal to uh, by the triangle inequality and the dilation, the scalar multiple property, right? So you have this less than or equal to basically what we call the subadditivity property. So we have this, right? 1 n equal to 1 to infinity. We have this, which is less than or equal to each norm xn is less than 1. So this is this, which is precisely 1 minus epsilon inverse. Okay. So this norm x is in this 1 minus epsilon inverse ball of radius 1 minus epsilon inverse. And what is Tx? Tx by the linearity, we have summation epsilon n minus 1 Txn, and Txn is precisely this. So this is Zn minus Zn minus 1, which is kind of which we know from this fact that the way we have constructed Zns, Zn minus Zs1, this will actually converge to the Z that we started with originally. So therefore, Z belongs to 1 minus epsilon inverse Tb1 epsilon, because Z is obtained as an image of X, where X is in this ball, right, which is which is 1 minus epsilon inverse dilation of the unit ball. So Z belongs to this ball, and Y is in this ball. That is how we started our y, right? Our y was coming from the image of the unit ball from here. Sorry, it is what we need to prove. Y is b1, y is from the unit ball of y. We need to show that y is in this, and we have shown that z is in that. So z is 1 minus epsilon inverse y. So z is in this ball, which means that 1 minus epsilon z, which is y, which is in this ball, and this is what we need to show, right? This is just from the definition of z, which gives you that y is in this. Therefore, we have shown this result. Okay, so we have shown, right? We have shown that whenever this closure contains this, then that set itself contains this ball of radius s. Now, using this is what we are going to show, what is called the open mapping theorem. The open mapping theorem is for when both x and y are complete norm space, Banach spaces, and T is a continuous linear operator, continuous linear map from x and from x to y, which is surjective. So it's an onto map. So it's onto y. That is Tx is equal to y, right? And so the codomain or the range of T is the entire y. If that happens, so for a continuous linear map, which is surjective between two Banach spaces, it's always an open map, which means it maps open sets to open sets. That is the open mapping theorem. So every continuous linear map between Banach space and every continuous linear surjective map between Banach spaces is an open map. So proof is we need to show that every open set is mapped to an open set. So without loss of generality, we will prove the result for the unit ball. Unit ball is an open set. We will show that the image of that is an open set, and it's enough to prove that because by the linear structure of the space, this can be extended to any open set. So we claim that omega is an open set in Y, the image of the unit ball. So by the linearity, it is enough to show that omega contains a ball around 0, right? So we have to show that omega open Y means for any point, we should find a ball which is completely contained in omega. It is enough to show, instead of showing it for every point, it's enough to show the point origin, because origin is in omega because it's the image of the origin in x. So it's enough to show a ball around origin, and by linearity that is enough. Also, we observe that this unit ball B1x is convex, so its image is also convex here because the map is a linear map here, right? This is also convex, and it's also symmetric about the origin, right? So you just reflect along the origin, you are that element is also in the set. If you take any element in the set, its reflection about the origin is also about the set. So both these properties are preserved. So omega is also, because the unit ball is convex and symmetric about the origin, its image omega is also convex and symmetric about the origin. Now if I take any ball of radius n in the ball of radius n centered at 0 in x, then its image is going to be the dilation of omega n by n. Okay, that this is again by the vector space structure of the which is by the underlying vector space structure, right? So and then the n omega closure is same as saying dilate the closure. Dilate the closure by n. That's what, right? Both these are again, all these follow from the vector space structure. So we are going to use all these results. So now we are given that T is surjective, which means for any y there is a x such that Tx is equal to y. This is by the surjectivity. So you start with any, if you take any y in y, there is an x in x, right? Now any such x has to sit in some dilation of the unit ball by some n, right? Which means that the y that you started with, which is the image of x, has to sit in n omega, because the image of unit ball is omega. So if x is in n b1x, then y is in n omega, again by linearity, right? So with this, what we have shown is that y can be written as union over n of n omega closure, right? That is because x is union of n n b1x closure, right? So and every element there is mapped here. So y is actually union of this, and y is a complete norm space, which is a Banach space. So y is a Banach space which is written as a countable union of some closed sets here, right? All these are closed sets. So by bare category theorem, one of them has to have non-empty. Uh, all of them cannot have empty interior. Otherwise, you have written it as a union of countable union of nowhere dense sets. So one of them has to have non-empty interior. So for some n, it has non-empty interior, which means that and each n omega closure is just the dilation of omega closure, which means that omega closure itself has non-empty interior. So the omega that we had here has non-empty interior. I mean, omega closure of this has non-empty interior. So you take any point in omega closure, let's call it y naught, and you take any r greater than 0, such that the ball of radius r centered at y naught is contained in omega closure. This is follows from the non-empty interior of omega closure. Now by symmetry, because we have already seen that omega is symmetric about the origin, by symmetry, if this ball is contained in omega bar, then the ball of radius r centered at minus y naught is also contained in omega bar, right? Similarly, by the convexity of right? This ball is contained here, this ball is contained centered at minus y naught is also contained here, and by convexity, that means all the points lying between them. So by convexity of all the points lying on the straight line joining between the points also lie in the set. So with the convexity of that, you can actually conclude that BR of uh, BR of the ball of radius r centered at origin is also in here, because y naught minus y, if you draw the line joining them, 0 is lying in that line, and this and so all the elements of radius r will also lie in this, because they will be lying in between the line joining the points from these two balls, right? So from this, and by using the previous lemma, we can conclude that BR of y is contained in omega, right? BR of y, we have started with BR of y not contained in BR of y not contained omega closure. So the previous lemma that we have obtained, it's actually contained in omega, and therefore omega is also right. This is why we require the previous lemma, where we had proved that if the closure contains the set, then the set itself contains the. Okay, so this is the open mapping theorem. As a corollary to that, we can do what is called the inverse mapping theorem, which tells you that if you have a continuous linear operator between two Banach spaces, and which is a bijective map, then the inverse is also continuous linear map. Okay, so this is the inverse mapping theorem. So this is a consequence of the open mapping theorem. Is a easy proof. So it's given that T is a bijection. continuous linear map, which is a bijection, which means T inverse exists, right? And it is also okay. Here when I say Lxy, so when we use the notation Bxy, I mean it is a continuous linear operator. When I say Lxy, I just mean it's a linear operator. Okay, so the inverse map exists because a bijection, the inverse is well defined, and the inverse map is actually a linear map. Okay, that can be verified by the fact that T itself is linear. Okay, so it's a linear map. What we need to show is that it's actually a continuous linear map. So we need to show the continuity of T inverse. Now with the open mapping theorem, right, T inverse is continuous, right? Why? Because this is a surjective map. T is a surjective map and it's an open map, right? By the open mapping theorem, T is open map. T is open map means T inverse is continuous because it maps open sets to open sets. So T inverse is going to, so for T inverse, to show the continuity of T inverse, T should map open sets to open sets, and that's what is following from the open mapping theorem. Therefore, T inverse is continuously bounded. Okay, and just a further observation that if further there is an R such that any ball of radius R is contained in the image of so not I mean not any ball of radius R, there is a radius R such that the ball of radius R is contained in the image of the unit ball. Okay, so this happens. So therefore, for all y in the unit ball of y, we can write it like this, right? Because it's just the dilation. So this BRY is just dilation of the unit ball. So RY is belonging to this RY. So if y belongs to unit ball, RY belongs to BRY0, right? So T inverse of RY is less than or equal to 1. This is from uh, this uh, this containment here, which actually gives you the exact norm, norm of the T inverse. So here we have shown that T inverse is actually bounded operator, and we are actually giving the bound as well here. Okay, it's less than or equal to 1 by R, where this R is such that the R was chosen such that this ball contains the image of the unit ball. So this is the inverse mapping theorem. Now, one application or easy consequence of this is that equivalence of norm between. So, if you have a vector space with two different norms, so here I've used double and triple lines to distinguish two different norms, and such that this vector space under this norm, this is actually a complete space, right? Complete norm space with respect to both the norms, it's complete. And if in addition the two norms satisfy this estimate, that is the triple norm of the x is less than or equal to C double norm of the x for all x, if this happens, then the two norms are equivalent. Okay, this is again a consequence of the open mapping theorem. So one of the norm is less than or equal to C times the other norm. This happens for all x, and if the space is a continuous if the space is a complete space, then these two norms are equivalent. Okay, so to prove the equivalence of norms, we already have one inequality, we just have to show the other inequality. To do that, you just look at the identity map, from x to x now, but you are giving the two different corresponding norms, which means you would have different topologies here, right? Different topology here. So you take the identity map. Now this identity map is a linear map, it's a bijection map, and it's a continuous map. Continuous map because that is what is given here. This condition basically means that this map, identity map from the double norm to triple norm, is continuous precisely, or bounded precisely means this inequality, right? So this inequality implies the continuity of the identity map. So the identity map is continuous bijection, linear map which is continuous and bijection. So by the inverse mapping theorem that we just proved some time back, uh, the inverse map is continuous by the open mapping theorem. Of course, that is from the open mapping theorem, because you have a bijection, so you have an inverse which is linear as always, because the original map is linear. Anyway, it's identity map, because inverse is also an identity map, but it's continuous because it's already a surjection. So this identity map is an open map, which means the inverse is a continuous map, right? And the continuity of the inverse precisely means this estimate, which means that the two norms are equivalent. Okay. So now using these functional, so far we have only done the abstract function analysis results, right? So using this function analysis results, we are going to show the stability of the two-point boundary value problem. Before that, what is stability? Stability of a differential equation or a system basically means that if you make a small change in the data, so in this case, what are the data? Datas are the one coming on the right hand side here, that is the source term here and the boundary terms. All these are datas. Here the boundary terms are 0 in this equation. So when the solution of the system uh, does not change arbitrarily, right? So any small change in data uh, kind of leads to a corresponding small change in the solutions. You cannot have a major change between. It's like if you think of the regulator of a fan or so on, right? So if there are 5 different speed settings of the fan, and if I do a kind of step-by-step change of the regulator, the fan accordingly increases the speed, right? Suppose if it's in 1, it's running very fast. At 5, it is running very slow, and like there is no uh, kind of nice dependence between them. Then it's not stable system. A stable system means that a small change in the source leads to a very it kind of I will not say the same small change. It is like a corresponding small change in the solution, right? You can actually calculate these things, right? All these are called stability or stability estimate. So what you see here, this estimate is the stability estimate. The solution is u here, right? So this is the f is the source here. So suppose I take say f1 minus f2, right? If I take f1 minus f2 here, then what you have here, the difference between two different solutions is bounded by the difference between the data here. So the difference between the solutions cannot really blow up or be very nasty, right? It is controlled by the difference between the change that you make. That is what stability means. Okay. And usually usually we study stable systems because stable systems are easier to understand and solve. I mean, easier to understand and probably easy to handle. Okay, so what is the stability of the two-point boundary value problem? So here we have second order ODE, and the two-point bound, as I already said about the two-point boundary value problem in the previous lecture, the boundary conditions are given. So the value of the solution is given at two different points. That in this case, the endpoints of the domain. Okay, which is why it's called boundary value problem. The value of the function is given on the boundaries. So this is a second order problem. The coefficients A, B, C are all continuous functions which is given to you, or these are also data. A, B, C is also data. So they are given. F is also given to you. Okay. F is also a continuous function on the domain. So they are all continuous function in the closed interval. Okay. Now what is given to us is that this problem, suppose say this problem has a unique solution, which is a twice differentiable function, right? So you have a twice differentiable function, sorry, solution to this problem, this ODE. Then there is a constant C such that the sum of the subnorms of the solutions of all the derivatives, so C2, right? So you take C2 means you have double derivative up to double derivative exists. So you take the sup of all that, right? And that is always less than or equal to C times the supremum norm of F. And this happens for all F and C, right? For every F. So when I say all F here, what I mean is that once you are given an F, you have a corresponding solution U. So if you change F, the U can change. So for every such correspondence, you have this inequality satisfied. So what is the proof of this? So to prove this, you define a space, a vector space X. So you look at the subset, you look at all elements of C201, that is all twice differentiable functions in the closed interval 0, 1. Take all functions such that V of 0 is 0 and V of 1 is 1. That is the boundary condition that is given to you. Basically, if U is a solution to this problem, then the U belongs to X here, right? So all possible solutions to this ODE for every possible choice of F is going to sit in this space X. Okay, so take this space X. You can verify that this is a vector space. Okay, you can verify easily that this X that you have defined here is a vector space. Now in this you give a norm. So we are going to define the norm. What is the norm? Because the C2 space, right? I'm going to define the norm. For instance, if I just define the subnorm of V, it will not make this a complete space. The subnorm of V makes the space of continuous functions complete. C2 of 0, 1 with the subnorm is actually a dense subset of C01, right? So to make this by itself a complete space, you actually define this norm up to, you just sum of the subnorms of V and its derivative up to the order that you have taken. So here you have taken C2, so you take up to the subnorm of the second derivative, up to second derivative. So you sum them. That is a norm that you give in this space X, and you can verify that with this norm, this X is going to be a complete norm space. Okay, so we are now in a complete norm space. Now we have a complete norm space X. This is precisely the solution space of this problem. If you, right, because any solution to this problem is going to lie in X. So this is the solution space of this problem. Now you define the operator T from X to C01 as this map. So T of V is A V prime. So basically the ODE part here, that is RHS of the ODE here. So you define TV to be this. So when you say you want to solve for U here, what you're asking is find all the V such that, so for any given F, find all V such that TV equal to F. That's what you are asking here. So this ODE is now seen as an operator. So this equation here is now seen as in terms of operator. That is, for every F in C01 here, do you have a solution Q such that TU is equal to, right? That's what this basically means, this correspondence means. And we are given that there is a unique solution to this problem, which means if I take any F here, there is a unique U here such that TU is equal to F is what this we have said here, admits a unique solution, which basically tells you that this T is surjective and injective, right? Right? By this fact that U is unique, you already have this fact that this T is surjective, because when we say for every F there is a solution, for every given F there is a solution U, basically means this T is surjective, right? And it's also one injective because you have exactly one solution, unique solution. So T is actually a bijection here. Okay. Okay. And also T is continuous or is bounded. Why? By the definition that we have here. By this definition, if I take norm of T, which is subnorm of T in C01, right? T of V will be in C01. Subnorm of T is norm of this entire thing, right? If you take the norm of this entire thing, you just now use take the norm, all the separate, use the triangle inequality and so on, and take the supremum over all this, or maximum over the subnorm of ABC. So if you take maximum of the subnorm of ABC, will come out. What will remain is the this norm, triple norm V. That will what will remain here, right? Which is what we want to show for. So this will happen for all V in X, which basically means that the norm of T is less than or equal to maximum of these coefficient norms. Okay, that's a simple thing from here. From here itself, you take norm, by Cauchy-Schwarz inequality, you see that this happens. So the norm of T is less than or equal to this. So T is continuous, T is bijection as well. So T is surjective, as I already said, T is surjective because there is a unique solution, and which means and the uniqueness of the because there is a solution for every f, and the uniqueness of the solution implies that it is injective, so it's a bijection. So it's a continuous bijection map. Okay. So now the inverse mapping theorem tells you that because the bijection T inverse exists, and by the inverse mapping theorem T inverse is continuous as well. Okay. And T inverse continuous is precisely the estimate that you want to. When you say T inverse is continuous, that means norm of T inverse satisfies something, right? And that is this, right? So if you take T inverse will be T inverse will take T inverse of f is less than or equal to T inverse of f is less than or equal to some C times f, right? And that is precisely what here. This is precisely T inverse of f, right? Because Tu is equal to f. So T inverse of f is precisely this quantity. So the stability estimate that we want to prove here is precisely the continuity property of the inverse operator, right? And that's what we have shown, that T inverse is actually bounded, means that there is a C such that this happens for all less than C0. Okay, so this is stability property of the 2-point boundary value property. Okay, so with this, I'll stop. We will meet in the next.